Have you ever picked up tiny pieces of paper with a plastic scale you just rubbed on your hair? You know, that classic childhood magic trick? You just vigorously rub the plastic, hold it over the paper, and suddenly the paper leaps right up, almost like an invisible magnet. Welcome to The Explainer. Today we're going to unpack exactly why that happens. Let's dive right in and demystify these abstract rules of the universe using simple, everyday analogies. In this explainer, we're taking a really close look at the fundamental properties of electric charges. We're going to take the incredibly complex physics of our reality and break it all down into simple, visual concepts that you can actually see in your mind's eye.
So, here is our roadmap for today. First, the magic of charge. Second, resting versus moving charges. Third, the three rules. Fourth, the invisible pull. And finally, reading the field.
Let's kick things off with Section 1, the magic of charge, specifically electrostatic induction. Now, what's really fascinating here is how a completely neutral object, like those tiny scraps of paper we talked about, can suddenly be drawn to a charged one, like your rubbed plastic scale. Think about it. The paper itself doesn't have an overall positive or negative charge. It is completely neutral. Yet, it reacts. This interaction is the cornerstone of a concept known as electrostatic induction. It's one of the most incredible phenomena in foundational physics because, well, it feels like magic, but it's purely driven by the fundamental properties of electric charges.
Let's break down exactly what happens inside that paper. Step 1, you bring the charge scale near the neutral paper. Step 2, the charges inside the paper kind of panic and redistribute. The charge scale pushes identical or like charges away to the far side of the paper, and it pulls the opposite charges as close as possible. Then, step 3. Because those opposite charges are now physically closer to the scale, their attractive pull wins out over the push of the repelled charges. Boom! Attraction happens without any direct contact whatsoever.
So, here is the absolutely crucial takeaway. Electrostatic induction only ever causes attraction between a charged and an uncharged object. You can never ever repel a completely uncharged object. Repulsion only happens if both objects are already charged with the exact same sign. Basically, if you see an object actively pushing away from another, you instantly know without a doubt that both objects possess a charge.
Moving right along to Section 2, resting versus moving charges.
To really simplify this complex physics, think of electrostatics as just carrying a bucket of water from one place to another. The water is largely resting inside the bucket. You might pick it up, transfer it to another room, just like how you transfer a static charge by rubbing a balloon on your sweater. It's a localized transfer. It holds energy in one place until it discharges. But electrodynamics, that is like the continuous, powerful flow of water rushing through the pipes in your house. That's electricity. That is the current powering the screen you're looking at right now. The charges are constantly running, driving energy from one place to another. Today, though, we're mostly focused on that bucket, the resting charges.
All right, Section 3, the three rules. These are the fundamental properties of charge. These are the absolute unbreakable rules of our universe. First up, additivity. You can just add charges together like basic math. 5 positive charges and 3 negative charges, that leaves you with 2 positive charges. Easy enough, right? Second, conservation. You cannot magically create or destroy a charge. You can only move it from one object to another. And third, quantization. This is the big one. It means charge only ever exists in strict, distinct packets. Just look at this incredibly small number, 1.6 times 10 to the power of negative 19 coulombs. It represents the elementary charge of a single electron. That is the absolute smallest packet of electric charge possible. It's a tiny, tiny fraction of a single coulomb, which is our standard unit of charge. Literally every single charged object in the universe, from your phone battery all the way to a massive lightning bolt, gets its charge by hoarding or losing exact multiples of this specific, tiny number. Think of it this way. Just like you can't have half a penny in your bank account, a charge cannot be a continuous random value. It must be a perfect multiple of that tiny electron packet. You can have 1 electron's worth of charge, or 2 trillion, but you can never, ever have 1.5 electrons worth of charge. No way! That is quantization. Nature literally forces charge to exist in distinct, non-continuous steps. Let's head into Section 4, the invisible pull, driven by Coulomb's law. The math behind this invisible pull is called Coulomb's law. It tells us that the push or pull between two charges is heavily dependent on the distance between them. But here is the real kicker. If you double the distance between two charges, the force doesn't just cut in half, it weakens by 4 times. If you triple the distance, the force weakens by 9 times. This inverse square rule is actually quite similar to how gravity works. The farther away you get, the pull drops off dramatically, scaling by the square of the distance rather than just a straight line.
But wait, how does a charge even know another charge is there in the first place? The answer is the electric field. Think of it as this invisible aura surrounding every charged particle. To measure this invisible field, we have to drop a tiny test charge into the space and just observe the force it experiences. It's exactly like throwing a single leaf into a river to see which way the current is flowing and how fast.
Now, the absolutely crucial point here is that our test charge has to be practically 0. Why is that? Well, if our test charge was too big, its own electric field would start pushing and pulling on the original charge we're trying to measure. It would totally mess up the very measurement we're trying to take. By making it infinitesimally small, we can perfectly map the field without disturbing it.
Finally, Section 5. Reading the field and looking at electric dipoles.
Let's specifically look at a dipole. A dipole is really just a positive and a negative charge stuck together by a small distance. Imagine dropping this dipole into a uniform electric field. When a dipole aligns perfectly with the flow of an electric field, it is in a stable equilibrium. It's like an egg lying flat on a table. Tap it and it just settles right back into place. But if you force that dipole to face the exact opposite way, directly against the field, that is unstable equilibrium. It's like balancing an egg perfectly on its tip. It might stay there for a split second, but the absolute slightest nudge will send it violently spinning and crashing down to realign itself.
Since we can't actually see these fields with our human eyes, physicists draw imaginary electric field lines to map out the exact pushing and pulling forces in an area. And these visual lines follow strict rules. They always blast outward from positive charges, and they dive straight into negative charges. They never, ever cross each other, because, well, a force can't push in 2 entirely different directions at the exact same point. And if you see a spot where the lines are drawn densely packed together, that tells you the invisible force right there is incredibly strong.
As we wrap up today's explainer, I want you to take a moment to just look around your room. Look at your desk, your computer, the walls. None of it is solid in the way we traditionally think. It is all held together by the massive, incredibly precise push and pull of positive and negative charges. So I leave you with this. What invisible, highly structured electric fields are pushing and pulling the atoms around you, holding your entire physical reality together at this very moment? It feels like magic, but it's physics. Keep wondering, keep learning, and we'll see you in the next explainer.